Okay, let's talk about electric fields. Electric fields is definitely one of those topics in IB and A-level physics that many students feel at a loss of understanding with. Not just because there are so many definitions and equations to remember and know how to use, but also due to the fact that we as people don't really encounter these concepts instinctively in day-to-day life, like we might Newton's laws of motion or the basic ideas of thermodynamics. Because these terms and concepts feel more alien to us, it's a topic that can easily overwhelm students and cost them precious marks in the exam. So, let's fix that. We're going to take a look at what I like to call the mountain analogy, which will be our way of connecting with the concepts behind all the key terms we need to know across electric fields. Let's say that we're looking at a mountain, with a point A at its peak and a point B at its foot. And let's say that there's a river flowing down this mountain from point A to point B. We can ask ourselves the question, what is it that makes the river flow down from A to B? Well, your first thought might jump straight to gravity, and you're not wrong. Gravity is involved and responsible for making the river rush down the mountainside with a current. But what is it exactly that gives gravity the ability to pull this water down? It's a bit of a trippy question, but here's the thing. Gravity gets taken for granted. It's so omnipresent in our day-to-day lives that we usually don't even notice it, or better yet, question its presence or how it causes things to move around us. For example, if a pencil was on a table and started rolling towards its edge, it's perfectly obvious to us what will happen the second there's no more table there to keep it from falling. Now, we might blame our little furry friend here for making the pencil fall, but really all the cat actually did was push the pencil forward until there was no more table left. The cat didn't oversee the process of bringing the pencil from the table to the ground. Gravity took on that job. So, if you think about it, all the cat did was give gravity the ability to step in and do its thing. And it's this gravity that will act on the pencil and perform work in physically dragging the pencil down to Earth. That's the key idea here. Things don't just move by themselves. Something has to make them move. When gravity acts on everything around us, we think it's perfectly expected, but in reality, gravity is exerting itself and makes an effort, i.e. work, to get the pencil to physically move from the height of the table to the height of the ground. Okay, back to our mountain. So, what is it exactly that gives gravity the ability to pull the river water down? Well, if you look closely, you'll realize that the river can only flow because there's a mountain there, right? So the physical presence of the mountain is what is allowing gravity to do work in dragging the water downhill. But what is it about the mountain? What does it provide specifically that allows it to help gravity wake up and act? The key idea here is that the mountain provides a difference in height. Point A gets to have a higher altitude than point B only because there is a mountain between them. And without this mountain, points A and B would be level with one another, and there'd be no context for gravity to make any water move between those 2 points. So our fast-flowing river would be nothing more than a puddle. Okay, now this might all feel a little obvious at this stage. So let's connect all these elements and concepts to the ones we encounter in electric fields. Our mountain is going to play the same role as our electric field. And just like the mountain is the physical structure that provides a difference in height between A and B, our electric field will provide a difference in what we call potential between these 2 points. Different positions in an electric field will have different values of potential, i.e. voltage. Just like different points along a mountain, by definition, will have different heights. So, where there is an electric field, there exists also a difference in potential. Just like where there is a mountain, there exists also a difference in height. So as we said, thanks to the difference in height provided by our mountain, gravity has a space to perform work in, acting on individual water molecules in the river to drag them down from A to B. Now, this is exactly what the electric force does on charged particles. We can think of fields as a space within which specific forces can be activated to act on specific particles. Effectively, if you have mass, you qualify for being acted on by the force of gravity. So if you find yourself in a gravitational field, gravity will act on your presence and make you move between 2 points of varying gravitational potential. Similarly, if you have charge, you qualify for being acted on by the electric force. So if you find yourself in an electric field, the electric force will recognize your charge and put in work to accelerate you accordingly between 2 points of different electric potential. So if our chosen particles happen to be a group of electrons, and they find themselves within an electric field at a point of a certain electric potential, like point A, the electric force can push these electrons down a potential gradient to another point of electric potential, like point B. And if electrons are made to move in a stream like this, an electric current is created in the opposite direction. Now, humans have leveraged the kinetic movement of rivers for centuries, tapping into them to harvest this energy for accomplishing other tasks that require work, such as using water mills to grind wheat, for example. Similarly, if we have a stream of electrons, we can dip our electric components, like light bulbs, into this flowing stream of electrons to harvest the electric current and activate our devices in a circuit. Okay, let's bring in some equations. Now that we've remembered that gravity needs to perform work, i.e. energy, in order to oversee the movement of particles with mass between points of different heights, we can ask ourselves, well, how much potential energy will gravity need to harvest to perform this effort? And where does it get this energy from exactly? Now, when we first encounter the concept of energy in physics, we usually learn about a type of energy called gravitational potential energy, the energy associated with an object's height above the ground. Gravitational potential energy is given by the equation E equals mg delta h, where m is our mass in kilograms, g is our acceleration due to gravity, and delta h is the change in height across which the object may be made to move by gravity. And effectively, gravity can harness and convert this potential energy into actual kinetic energy in making the mass move across this displacement delta h. So the total energy gravity has available to perform work is given by this equation. And conveniently for us, our analogy transfers over into the electric field chapter. So here, the work done by the electric force is given by not the mass, but the charge of our particle, and the difference in potential between the 2 points this force will carry this charged particle across. Now, you can probably tell that between points A and B, regardless of what path the river might take, as long as it starts from A and flows to B, be it slowly or quickly, gravity only ever has that same total amount of energy to use to do work. So as long as we start at point A and end at point B, the work done by gravity is the same, regardless of the path taken from A to B. This is exactly the same for the electric force. Whatever the path the charged particle is made to take between 2 points of different potential, the electric force still only has the same finite amount of electric potential energy between those points to use to perform work. So work done is independent of the path taken.